Picture this. You're staring up at the full moon on a clear night, admiring that familiar face we've known since childhood. Those dark patches that form what some see as a man in the moon, the bright highlands that create intricate patterns across its surface. But here's what will blow your mind. Everything you're looking at represents only half of our closest celestial neighbor. There's an entire hemisphere of the moon that remains forever hidden from our view, shrouded in mystery and scientific intrigue. And NASA's recent discoveries about this hidden realm are about to completely reshape everything we thought we knew about our cosmic companion. What I'm about to reveal to you isn't just another space story. This is a tale of groundbreaking discoveries, technological marvels, and scientific revelations that are literally rewriting textbooks as we speak. We're talking about findings so significant that they're forcing scientists to reconsider fundamental theories about how our moon formed, evolved, and continues to influence our planet today. But before we dive into these mind-bending discoveries, we need to address one of the most persistent misconceptions in all of astronomy. The phrase "dark side of the moon" has captured imaginations for generations, inspiring everything from Pink Floyd albums to countless science fiction stories. Yet this term is fundamentally misleading, and understanding why is crucial to appreciating the true mystery of what lies on the moon's hidden hemisphere. The moon doesn't actually have a permanently dark side. What we're really talking about is the far side of the moon, a hemisphere that remains perpetually turned away from Earth due to a fascinating gravitational phenomenon called tidal locking. This cosmic dance means that while one side of the moon basks in sunlight for roughly 2 weeks, the other side experiences its own day-night cycle. In fact, when you add up all the hours of direct and indirect sunlight exposure throughout a lunar month, the far side actually receives slightly more illumination than the side we can see from Earth. So why does this hemisphere remain invisible to us? The answer lies in the intricate gravitational relationship between Earth and the moon. Tidal locking has synchronized the moon's rotation with its orbit around our planet, creating a cosmic choreography that takes exactly 28 days to complete. This means that as the moon orbits Earth, it rotates at precisely the same rate, ensuring that the same hemisphere always faces our planet, while the other remains forever hidden from our direct view. This invisible hemisphere has tantalized scientists for decades, representing one of the last great frontiers in our immediate cosmic neighborhood. Unlike the familiar near side with its distinctive dark patches called Maria, ancient lava plains that formed billions of years ago, the far side presents a dramatically different landscape that has remained largely mysterious until recently. For most of human history, we could only speculate about what lay beyond our line of sight. The far side existed in our imagination as a realm of possibilities, a blank canvas upon which we projected our wildest theories and most ambitious dreams. Some wondered if it might harbor alien bases or ancient structures. Others theorized about unique geological formations that could unlock secrets of planetary formation. The reality, as we're about to discover, is far more fascinating than any science fiction story. The breakthrough moment came when NASA's Deep Space Climate Observatory satellite achieved something remarkable, capturing unprecedented images of the moon's far side from a vantage point roughly 1 million miles away from Earth. These weren't just any photographs. They represented humanity's first clear, comprehensive view of the hidden hemisphere in full sunlight, with our brilliantly lit Earth serving as a dramatic backdrop. What these images revealed was absolutely stunning. The far side of the moon presented a landscape so different from the familiar near side that scientists initially questioned whether they were looking at the same celestial body. Where the near side features those prominent dark Maria that create the man in the moon pattern we all recognize, the far side displayed a heavily cratered, ancient surface dominated by impact basins and towering mountain ranges. The contrast was so dramatic that it raised immediate questions about the moon's formation and evolution. How could two halves of the same object be so fundamentally different? The near side hosts 93% of the Moon's basaltic plains, while only 7% lie on the far side. This stark asymmetry suggested that the Moon's geological history was far more complex and dynamic than anyone had previously imagined. But these initial observations were just the beginning. The real breakthrough came when China achieved something that no nation had ever accomplished before, successfully landing a spacecraft on the far side and bringing back samples from this mysterious realm. The Chang'e 6 mission didn't just make history, it opened an entirely new chapter in lunar science and our understanding of planetary formation. The mission itself was a masterpiece of engineering precision. Landing on the far side of the Moon presents unique challenges that don't exist for near-side missions. The most significant obstacle is communication. When you're operating on the hemisphere that faces away from Earth, radio signals simply cannot reach your spacecraft directly. The Moon itself acts as a massive barrier, blocking all communication attempts. To overcome this challenge, China deployed a relay satellite called Kuehiao-2, positioned at a special gravitational balance point where it could maintain constant communication with both Earth and the landing site. This technological innovation made possible what had previously been impossible: sustained operations on the lunar far side. The landing site was carefully chosen for maximum scientific value. The Chang'e 6 lander touched down in the southern portion of the Apollo crater, which sits within the much larger South Pole Aitken Basin. This location wasn't selected randomly. It represents one of the most scientifically significant regions on the entire Moon. The South Pole Aitken Basin is the largest, deepest, and oldest impact structure on the lunar surface, possibly the largest impact crater in the entire solar system. This massive impact structure, created by an asteroid collision billions of years ago, potentially excavated material from deep within the Moon's interior and scattered it across the surrounding landscape. Scientists theorize that samples from this region might contain fragments of the lunar mantle, material from deep inside the Moon that had never been accessible to previous missions. Over the course of several days, the Chang'e 6 lander methodically collected samples using both surface scoops and subsurface drilling techniques. The precision required for this operation was extraordinary. Every movement had to be carefully planned and executed, with commands traveling from Earth to the relay satellite and then to the lander, introducing significant delays that made real-time control impossible. The samples themselves totaled just under 2 kilograms of material, but their scientific value was immeasurable. These fragments of rock and soil represented humanity's first direct look at the composition and history of the Moon's hidden hemisphere. After careful collection and storage in a specially designed container, the samples began their journey back to Earth aboard the mission's ascent stage. The return journey was equally challenging, requiring precise timing and navigation to rendezvous with the orbiting spacecraft and eventually make the long trip back to our planet. When the sample container finally parachuted to Earth after a 53-day mission, it carried within it the potential to revolutionize our understanding of lunar science. The initial analysis of these far-side samples immediately revealed surprises that challenged existing theories about lunar evolution. The rocks showed a complex geological history that differed significantly from near-side samples collected during the Apollo missions decades earlier. The age dating revealed basalt fragments that formed 2.8 billion years ago, suggesting that volcanic activity on the far side continued much longer than scientists had previously believed possible. But perhaps the most shocking discovery was a single basalt fragment that dated back 4.2 billion years, making it one of the oldest pieces of lunar material ever analyzed. This ancient rock fragment provided a window into the Moon's earliest geological processes and raised fundamental questions about how long the Moon remained molten after its formation. The composition of these samples also revealed unexpected characteristics. Unlike many Apollo-era samples, the Chang'e 6 materials showed different concentrations of key elements, suggesting that the processes that shaped the far side were fundamentally different from those that created the familiar landscape we see from Earth. These discoveries represent just the beginning of what promises to be a revolutionary period in lunar science. The samples are still being analyzed in laboratories around the world, with each new finding potentially reshaping our understanding of not just the Moon, but the entire early solar system. The implications extend far beyond lunar science. The Moon serves as a natural laboratory for understanding planetary formation processes throughout the universe. The lack of atmosphere and geological activity means that the lunar surface preserves a record of events that occurred billions of years ago, offering insights into the violent early period when planets were still forming and massive impacts were common. As we continue to analyze these precious samples and plan future missions to explore the far side more extensively, we're standing at the threshold of a new era in space exploration. The mysterious far side is revealing its secrets, and each discovery brings us closer to understanding our place in the cosmic story that began over 4.5 billion years ago. What makes these far side discoveries even more extraordinary is the revelation of something scientists call creep basalts, a discovery that's forcing researchers to completely reconsider how the Moon formed and evolved. Creep stands for potassium, rare earth elements, and phosphorus, materials that generate heat and help explain why volcanic activity continued on the Moon far longer than anyone expected. For decades, scientists believed that creep basalts existed only on the near side of the Moon, concentrated in specific regions like Oceanus Procellarum and Mare Imbrium. This distribution supported various theories about lunar formation, including the controversial Big Splat hypothesis. This theory suggested that our Moon actually formed from the collision and merger of two separate moons, a larger primary moon and a smaller secondary moon that eventually pancaked into the larger body, creating the thicker crust we observe on the far side. But the Chang'e 6 samples have turned this theory completely upside down. Among the collected materials, scientists discovered a 4.2 billion-year-old creep basalt fragment that displays pristine magmatic texture without any impact-induced fractures. This finding provides compelling evidence that the ancient creep-rich material originated directly within the Apollo basin, not from some distant impact or secondary collision. The implications of this discovery ripple through our entire understanding of lunar evolution. If creep basalts are native to both sides of the Moon, then the second moon hypothesis, along with several other lunar formation theories, may need to be completely abandoned. We're witnessing scientific theories that have stood for decades crumble in the face of new evidence, forcing researchers to go back to the drawing board and develop entirely new models for how our celestial companion came to be. But the mysteries don't stop there. Hidden beneath the far side's heavily cratered surface lies a network of geological features that challenge everything we thought we knew about lunar structure and activity. Advanced gravitational mapping missions, particularly NASA's GRAIL project, have revealed massive concentrations of dense material buried deep beneath the far side. Structures known as mascons that could represent the remnants of ancient asteroid impacts or evidence of volcanic activity that occurred billions of years ago. These subsurface anomalies paint a picture of a Moon that's far more geologically complex than the dead, inactive world we once imagined. Seismic studies have identified thick, dense layers deep beneath the surface that likely represent fragments of the Moon's primordial crust, material that has remained largely unchanged since the Moon's formation over 4 billion years ago. Even more intriguing are the magnetic anomalies scattered across the far side's landscape. The Moon currently lacks a global magnetic field like Earth's, but sensitive instruments have detected localized regions of intense magnetism that tell a fascinating story about the Moon's ancient past. These magnetic signatures appear to be concentrated near major impact basins, suggesting a connection between catastrophic collisions and the preservation of ancient magnetic fields. The leading theory proposes that when massive asteroids slammed into the Moon billions of years ago, The impacts created such intense heat and pressure that metallic iron within the asteroid material became magnetized as it cooled. These impact events essentially created permanent magnetic recordings of whatever global magnetic field the Moon possessed at the time of collision, like cosmic time capsules preserving evidence of the Moon's magnetic history. Or some of these magnetic anomalies are so strong that they may actually be protecting nearby regions from solar wind erosion, creating unique microenvironments that have preserved ancient materials for billions of years. Scientists speculate that these magnetically shielded areas might contain the most pristine examples of early lunar material, offering unprecedented insights into the Moon's formation and early evolution. The far side is also home to extensive networks of ancient lava tubes, underground tunnels carved by volcanic flows that occurred billions of years ago. Advanced radar imaging has revealed these subterranean chambers stretching for miles beneath the surface, creating vast hollow spaces that remained hidden until recently. These natural caverns represent more than just geological curiosities. They could serve as ready-made shelters for future lunar explorers, providing protection from radiation, micrometeorite impacts, and the extreme temperature variations that characterize the lunar surface. Perhaps most fascinating of all is the discovery that some areas of the far side may still be geologically active. Sensitive instruments have detected complex networks of subsurface faults and tectonic fractures that suggest ongoing geological processes deep within the lunar interior. This finding contradicts the long-held belief that the Moon is completely geologically dead, instead revealing a world where subtle but significant changes may still be occurring beneath the ancient cratered surface. The South Pole Aitken Basin, where Chang'e 6 collected its historic samples, represents the crown jewel of far-side geological features. This massive impact structure stretches over 1,200 miles across and plunges more than 8 miles deep, making it one of the largest impact craters in the entire solar system. The sheer scale of this ancient scar provides a window into the violent bombardment period that characterized the early solar system, when massive asteroids and comets regularly collided with planetary surfaces. What makes this basin particularly valuable for scientific research is its potential to contain material from the Moon's deep interior. The impact that created this enormous crater was so powerful that it likely punched through the lunar crust entirely, excavating and scattering mantle material across the surrounding landscape. This means that the Chang'e 6 samples might actually contain fragments from deep within the Moon, material that would normally be completely inaccessible to surface missions. The age and composition of these deep materials could provide crucial insights into the Moon's internal structure and formation processes. Scientists are particularly interested in understanding how the Moon's interior differentiated, how heavier materials sank toward the center, while lighter materials rose toward the surface. This process occurred billions of years ago when the Moon was still largely molten, and the evidence preserved in South Pole Aitken Basin materials could help reconstruct this critical period in lunar history. Current analysis of the Chang'e 6 samples is revealing layer upon layer of complexity in the Moon's geological record. Each rock fragment tells a story about different periods in lunar history, some preserving evidence of the earliest volcanic activity, others recording the signatures of massive impact events, and still others containing clues about the chemical evolution of the lunar interior over billions of years. The thermal history revealed by these samples is particularly intriguing. The discovery that volcanic activity continued on the far side until at least 2.8 billion years ago suggests that the Moon remained partially molten for much longer than previously thought. This extended period of geological activity requires a heat source that scientists don't fully understand. The radioactive elements that powered early lunar volcanism should have decayed to much lower levels by that time. One possibility is that the far side's thicker crust acted as an insulating blanket, trapping heat within the lunar interior and allowing volcanic processes to continue long after they ceased on the thinner crusted near side. Another theory suggests that the distribution of heat-generating elements within the moon was far more complex than current models predict, with concentrations of radioactive materials creating localized hotspots that sustained volcanic activity in specific regions. These discoveries are revolutionizing our understanding of not just the moon, but planetary formation processes throughout the solar system. The moon serves as a natural laboratory for studying the early conditions that shaped all terrestrial planets, including Earth. Because the moon lacks plate tectonics and has minimal atmospheric weathering, its surface preserves a detailed record of events that occurred during the solar system's chaotic youth. A record that has been largely erased on more geologically active worlds like Earth and Mars. The far-side samples are also revealing evidence of impact processes that shaped the entire inner solar system during a period scientists call the Late Heavy Bombardment. This was a catastrophic era roughly 4 billion years ago when a sudden surge of asteroid and comet impacts pummeled the Moon, Earth, Mars, and other terrestrial planets. The timing and intensity of this bombardment has been hotly debated, but the Chang'e 6 materials are providing new clues about when it occurred and how it influenced planetary evolution. What's particularly fascinating is that the far side appears to have preserved a more complete record of this bombardment than the near side. The thicker crust and reduced volcanic resurfacing means that ancient impact signatures remain largely intact, like a cosmic archaeological site that's been waiting billions of years for us to discover it. Each impact basin tells a story about the size, composition, and trajectory of the objects that created them, building a detailed picture of the solar system's violent adolescence. The chemical signatures within these ancient impact materials are revealing surprises about the composition of early solar system objects. Some samples contain isotopic ratios that don't match typical lunar materials, suggesting they preserve fragments of the original impacting asteroids and comets. This extraterrestrial material, now embedded within lunar samples, provides direct evidence of the objects that were flying around the inner solar system billions of years ago. Even more intriguing is the discovery of what scientists are calling impact glass, materials that were melted and rapidly cooled during ancient collisions. These glassy fragments preserve magnetic signatures that are far stronger than anything the Moon's weak internal magnetic field could have produced. The magnetism appears to be generated by the impact process itself, as the tremendous energies involved in these collisions created temporary magnetic fields that became permanently recorded in the cooling debris. This finding is revolutionizing our understanding of how magnetic fields can be generated on airless bodies like the Moon. Previously, scientists assumed that strong magnetism required either an active dynamo in a planet's core or interaction with stellar magnetic fields. But these impact-generated magnetic signatures suggest an entirely new mechanism for creating and preserving magnetism on planetary surfaces. The implications extend far beyond the Moon. Similar impact processes occurred on Mars, Mercury, and the large asteroids, meaning these worlds might also harbor hidden magnetic records of ancient collisions. Future missions to these bodies might uncover similar magnetic time capsules that preserve evidence of solar system conditions billions of years ago. But perhaps the most mind-bending discovery emerging from far-side research involves the detection of subsurface structures that suggest the Moon's interior is far more complex than anyone imagined. Deep radar penetration studies have revealed what appear to be massive chambers and cavities beneath the surface. Not just the lava tubes we discussed earlier, but enormous hollow spaces that might represent ancient magma chambers or even stranger geological formations. Some of these subsurface voids are truly enormous, spanning hundreds of miles and extending deep into the lunar crust. The discovery of such large empty spaces raises fundamental questions about the Moon's internal structure and formation. How did these cavities form? Are they connected to ancient volcanic processes, or do they represent something entirely different? One particularly intriguing possibility is that these hollow regions preserve evidence of the Moon's earliest differentiation processes. When the moon first formed, it was likely a completely molten ball of rock and metal. As it cooled, heavier materials sank toward the center, while lighter materials rose to form the crust. But this process might not have been as simple or uniform as scientists previously assumed. The subsurface cavities could represent regions where this differentiation process created temporary instabilities, areas where rising or sinking materials left behind hollow spaces that were never filled. If this theory is correct, these voids might contain unique materials that preserve evidence of the moon's formation in ways that surface rocks cannot. The technological challenges of exploring these subsurface mysteries are driving incredible innovations in space exploration technology. Future missions are being designed with ground-penetrating radar systems that can map the three-dimensional structure of the lunar interior in unprecedented detail. These instruments will create detailed cross-sections of the moon's hidden architecture, revealing the full extent of these mysterious underground formations. NASA's Artemis program is specifically targeting regions of the far side for detailed exploration, with plans to deploy robotic rovers equipped with advanced subsurface imaging systems. These missions will work in conjunction with orbiting spacecraft to create comprehensive maps of both the surface geology and the hidden structures beneath. The communication challenges that make far-side exploration so difficult are also spurring innovations in satellite relay technology. Future missions will deploy networks of small communication satellites around the moon, creating a permanent infrastructure that will enable continuous contact with surface operations, regardless of their location on the lunar surface. This communication network will support not just scientific missions, but also the eventual establishment of permanent human outposts on the far side. The unique radio-quiet environment of the far side makes it an ideal location for astronomical observations that would be impossible on Earth or even on the moon's near side. Free from the radio interference generated by human technology on Earth, telescopes on the far side could detect incredibly faint signals from the early universe. The concept of a far-side radio telescope represents one of the most ambitious scientific projects currently under serious consideration. Engineers have designed plans for a massive radio antenna system that would be constructed in one of the far side's ancient impact craters, creating a natural bowl-shaped receiver that could capture radio waves from the cosmic dawn, the period shortly after the Big Bang when the first stars and galaxies were forming. This telescope would be capable of detecting signals that are completely impossible to observe from Earth due to our planet's radio-noisy environment. It could potentially observe the universe during periods that remain completely mysterious to current astronomy, filling in crucial gaps in our understanding of cosmic evolution. The scientific discoveries emerging from far-side exploration are also raising profound questions about the nature of planetary formation throughout the universe. If our moon, which we've studied intensively for over 50 years, can still surprise us with such fundamental revelations, what might we discover when we begin serious exploration of the moons orbiting other planets in our solar system? Jupiter's moon Europa and Saturn's moon Enceladus both show evidence of subsurface oceans beneath icy crusts, but we know virtually nothing about their internal structure or geological processes. The techniques being developed for far-side exploration, subsurface imaging, sample return from difficult locations, and remote operation in communication-restricted environments will be directly applicable to future missions to these distant worlds. The Chang'e 6 mission has also demonstrated that sample return missions to challenging locations are not only possible, but can be executed with remarkable precision and success. This technological achievement opens the door to sample return missions from Mars, asteroids, and even the outer planet moons. Missions that seemed impossibly difficult just a few years ago. The far-side discoveries are fundamentally changing how we think about the moon's role in Earth's history and development. The magnetic anomalies and impact records preserved on the far side provide insights into the early solar system environment that influenced Earth's own formation and evolution. The timing and intensity of the late heavy bombardment, for example, had profound implications for the development of life on our planet. Some scientists speculate that the massive impacts recorded in far-side geology might have delivered water and organic compounds to the early Earth, providing the raw materials necessary for life to emerge. Others suggest that these same impacts might have temporarily sterilized planetary surfaces, creating a complex pattern of destruction and renewal that ultimately shaped the conditions for biological evolution. The age relationships revealed by Chang'e 6 samples are providing new constraints on these theories, helping scientists understand the precise timing of events that influenced Earth's early development. This connection between lunar and terrestrial history illustrates how the Moon serves not just as a fascinating world in its own right, but as a crucial archive of information about our own planet's past. As we continue to analyze the treasures returned by Chang'e 6 and plan increasingly ambitious missions to explore the far side more comprehensively, we're entering an era where the Moon's hidden hemisphere is becoming less mysterious and more scientifically accessible than ever before. Each new discovery builds upon previous findings, creating an increasingly detailed picture of lunar evolution that challenges our assumptions and expands our understanding of planetary science. The journey to understand the far side is far from over. In fact, we're just beginning to scratch the surface of what this hidden realm has to teach us about the solar system's history, planetary formation processes, and the complex relationships between celestial bodies that have shaped our cosmic neighborhood for billions of years. The revelations emerging from far-side exploration are forcing us to confront a humbling reality about our cosmic understanding. Despite decades of lunar study, satellite observations, and the wealth of data collected during the Apollo era, we're discovering that our Moon harbors secrets that challenge the very foundations of planetary science. The far side isn't just geologically different from the near side, it's revealing that our entire conceptual framework for understanding how rocky worlds form and evolve may be fundamentally incomplete. Recent thermal imaging studies conducted by orbiting spacecraft have detected temperature anomalies beneath the far side surface that suggest ongoing geological processes. These aren't the subtle temperature variations you might expect from a dead world slowly radiating away its primordial heat. Instead, scientists are observing localized hotspots that appear to be actively changing over time, indicating that something dynamic is happening deep within the lunar interior. The most compelling evidence comes from a series of measurements taken over several years that show certain regions experiencing cyclical temperature changes that can't be explained by solar heating alone. These variations follow patterns that suggest internal heat sources are occasionally becoming more or less active, almost as if the Moon's deep interior is experiencing some form of geological breathing. This discovery has profound implications for our understanding of small planetary bodies throughout the solar system. If the Moon, which we've long considered a relatively simple, geologically inactive world, can maintain internal heat sources for over 4 billion years, then our assumptions about the thermal evolution of rocky planets and large asteroids may need complete revision. The mechanism driving this apparent ongoing activity remains one of the most intriguing mysteries in current lunar science. Traditional models suggest that a body the Moon's size should have cooled to near complete geological inactivity billions of years ago. The radioactive elements that powered early volcanism should have decayed to levels too low to maintain significant heating, and the Moon lacks the tidal heating that keeps some of Jupiter's and Saturn's moons geologically active. Yet something is clearly generating enough heat in specific regions to create detectable temperature anomalies. One possibility involves previously unknown concentrations of long-lived radioactive elements deep within the lunar interior. Another theory suggests that the complex internal structure revealed by gravitational mapping studies might create conditions where heat becomes trapped and concentrated in unexpected ways. The gravitational data itself tells a fascinating story about the Moon's hidden internal architecture. The Grail mission's detailed mapping revealed that the lunar interior is far more heterogeneous than anyone anticipated. Instead of the relatively simple layered structure predicted by early formation models, The Moon appears to contain a complex network of dense and less dense regions that create intricate patterns of gravitational variation. These gravitational anomalies aren't randomly distributed. They show clear correlations with surface features, particularly the major impact basins that dominate far-side topography. The largest anomalies correspond to the deepest and oldest impact structures, suggesting that these ancient collisions didn't just reshape the surface, but fundamentally altered the Moon's internal structure in ways that persist today. The most dramatic example is the gravitational signature associated with the South Pole Aitken Basin. The impact that created this enormous crater appears to have excavated so much material that it permanently altered the distribution of mass within the Moon. Dense materials from deep within the lunar interior were exposed and redistributed, while lighter crustal materials were scattered across vast distances. But here's where the story becomes even more fascinating. The gravitational data suggests that this redistribution of materials wasn't a one-time event. Follow-up analysis indicates that the basin's gravitational signature has subtle variations that might reflect ongoing settling or adjustment of materials within the impact structure. It's as if the Moon is still slowly recovering from this ancient catastrophic event, with internal materials continuing to shift and adjust billions of years after the original collision. This concept of long-term geological memory challenges our understanding of how planetary bodies respond to major impacts. We typically think of impact events as instantaneous geological catastrophes that reshape surface features, but leave internal structure largely unchanged. The far-side data suggests instead that major impacts create lasting instabilities that continue to influence internal processes for geological ages. The implications extend to impact processes throughout the solar system. Mars shows evidence of ancient impact basins that rival the scale of the South Pole Aitken structure. Mercury's surface is dominated by impact features that must have created similar internal disruptions. Even Earth, despite its active geology, likely experienced comparable impacts during the late heavy bombardment that may have influenced our planet's internal evolution in ways we're only beginning to understand. The chemical analysis of Chang'e 6 samples is revealing additional layers of complexity in the far side's geological story. Beyond the age relationships and creep signatures we discussed earlier, detailed isotopic studies are uncovering evidence of chemical processes that don't fit standard models of lunar evolution. Some samples contain isotopic ratios that appear to record interactions between different types of materials within the lunar interior. These signatures suggest that the Moon's internal differentiation, the process by which heavy materials sank toward the center while light materials rose to form the crust, was far more complex and prolonged than previously understood. Traditional models assume that differentiation occurred relatively quickly after the Moon's formation, with most of the process completed within the first few 100 million years. But the isotopic evidence from far-side samples suggests that chemical exchange between different internal layers continued for much longer, possibly extending well into the period when Chang'e 6's oldest samples were forming over 4 billion years ago. This extended differentiation timeline has significant implications for understanding how heat was distributed within the early Moon. If materials were still mixing and separating billions of years after formation, then heat-generating radioactive elements may have been redistributed in ways that created long-lasting hotspots in unexpected locations. This could help explain both the prolonged volcanic activity recorded in far-side samples and the thermal anomalies being detected by current orbital missions. The discovery of complex organic molecules within some Chang'e 6 samples has opened yet another avenue of investigation. While these organic compounds almost certainly don't indicate biological activity, their presence raises intriguing questions about the delivery of carbon-based materials to the early Earth-Moon system. The organic molecules appear to be concentrated in materials that show clear evidence of impact processing, suggesting they were delivered by the same asteroids and comets that created the far side's heavily cratered landscape. This finding supports theories that the late heavy bombardment wasn't just a period of destruction, but also served as a delivery mechanism for the volatile compounds necessary for planetary atmosphere formation, and possibly even the emergence of life. The specific types of organic molecules detected in the samples include complex carbon chains and ring structures that are known to form in the cold, radiation-rich environments of deep space. Their preservation within lunar samples suggests that the Moon's surface has acted as a natural repository for materials from throughout the early solar system, collecting and preserving chemical signatures that have been lost from more geologically active worlds. Some of these organic compounds show isotopic signatures that don't match typical solar system materials, hinting that they may have originated from interstellar sources. Organic molecules that formed in the space between stars before being incorporated into the solar system during its formation. If confirmed, this would represent direct evidence of interstellar organic chemistry preserved within lunar geology, providing unprecedented insights into the chemical conditions that existed during the solar system's birth. The magnetic anomaly studies are revealing equally surprising complexity in the far side's magnetic landscape. High-resolution mapping has identified magnetic signatures that appear to be organized in patterns that correlate with ancient impact structures. But the relationships are far more intricate than simple impact-generated magnetization. Some magnetic anomalies show evidence of multiple magnetic recording events, as if the same rocks were magnetized, demagnetized, and remagnetized several times throughout lunar history. This suggests that the early Moon may have experienced multiple periods of internal magnetic field generation, possibly related to different phases of core evolution or external magnetic influences from the early Sun. Even more intriguingly, some of the strongest magnetic signatures appear to be associated with subsurface structures rather than surface features. Deep penetrating magnetic surveys have identified intense magnetic anomalies that have no clear correspondence with visible geology, suggesting the presence of highly magnetized materials buried beneath the surface. These buried magnetic sources could represent fragments of the original impacting asteroids that created the far side's major basins. If large metallic cores from these ancient impactors remain buried beneath the surface, they could preserve magnetic recordings of solar system conditions from over 4 billion years ago. Each buried fragment would act like a geological compass needle, pointing in the direction of whatever magnetic field existed at the time of impact. The possibility of recovering such ancient magnetic records has scientists planning increasingly sophisticated missions to map and eventually sample these buried magnetic anomalies. Future drilling missions might be able to extract cores that contain metallic fragments from the original impacting bodies, providing direct access to materials that formed in entirely different regions of the early solar system. The lava tube networks discovered beneath the far side's surface are proving to be far more extensive than initial surveys suggested. Advanced radar mapping has revealed interconnected systems of underground channels that stretch for hundreds of miles, creating a hidden transportation network beneath the lunar surface. These natural tunnels aren't just geological curiosities. They represent perfectly preserved records of ancient volcanic activity that occurred when the Moon was still geologically active. The walls of these lava tubes contain layer upon layer of volcanic deposits that record different episodes of eruption and flow, creating a detailed timeline of far-side volcanism that spans billions of years. Some lava tubes appear to connect different regions of ancient volcanic activity, suggesting that the far side's magma systems were far more interconnected than the surface geology alone would indicate. This underground connectivity could explain how volcanic activity persisted in some regions long after it ceased in others. Magma could travel through these subsurface networks to reach the surface in locations far from the original heat sources. The preservation conditions within these lava tubes are extraordinary. Protected from micrometeorite bombardment, solar radiation, and temperature extremes, the tube interiors maintain nearly pristine examples of ancient lunar volcanic materials. Future missions that can access these underground chambers may discover volcanic glasses, mineral crystals, and gas bubble structures that provide unprecedented details about the conditions and processes that drove far-side volcanism. But perhaps the most exciting possibility involves the discovery of what scientists are calling pristine impact melt within some lava tube systems. These appear to be materials that were melted during ancient impact events, but flowed into underground cavities where they cooled slowly and remained undisturbed for billions of years. Unlike the rapidly cooled impact glasses found on the surface, these slowly cooled impact melts preserve detailed mineral textures and chemical gradients that record the exact conditions during ancient collision events. They essentially represent natural laboratories where impact processes can be studied in extraordinary detail, providing insights into the physics and chemistry of catastrophic collisions that shaped the early solar system. The scale and complexity of far-side geology continues to surprise researchers as new data becomes available. Recent analysis suggests that the heavily cratered far-side landscape isn't just the result of random impact bombardment, but shows evidence of systematic patterns that might reflect the orbital dynamics of the early solar system. The size distribution and spatial arrangement of impact craters appears to follow patterns that could indicate preferential impact directions or systematic variations in the types of objects that collided with the far side. Some researchers are investigating whether these patterns preserve evidence of ancient asteroid streams or comet showers that affected the entire inner solar system during specific periods of early solar system evolution. If confirmed, these impact patterns could provide crucial constraints on models of early solar system dynamics, including the orbital evolution of the giant planets and the timing of events like the late heavy bombardment. The far side's crater record might serve as a natural observatory that recorded the gravitational choreography of the early solar system in ways that no other evidence can provide. The ongoing analysis of Chang'e's 6 samples continues to yield surprises that challenge established theories about lunar evolution. Recent findings include evidence of multiple distinct magma compositions within individual rock samples, suggesting that the far side experienced more complex volcanic processes than previously understood. Some samples appear to contain materials from different depths within the lunar interior, mixed together in ways that indicate vigorous convection and magma mixing occurred during certain periods of lunar history. This evidence for dynamic internal processes contrasts sharply with models that assumed the moon's interior was relatively static after the initial differentiation period. The chemical signatures within these mixed materials are providing new insights into the composition and behavior of the lunar interior during different phases of evolution. They suggest that the boundary between the lunar core and mantle may have been more dynamic than previously thought, with materials occasionally exchanging between these different internal regions. This evidence for ongoing internal mixing has implications for understanding how heat was distributed within the moon throughout its history. If convection occasionally brought hot materials from deep within the interior closer to the surface, it could help explain how volcanic activity persisted long after conventional models predict it should have ceased. The revelations emerging from far-side exploration represent just the beginning of a revolution in lunar science. Each new discovery raises additional questions and suggests new avenues for investigation. The hidden hemisphere that remained mysterious for so long is finally revealing its secrets. But those secrets are proving to be far more complex and fascinating than anyone anticipated. As we prepare for the next phase of lunar exploration, with human missions returning to the moon and robotic explorers venturing into the most remote and challenging locations on the far side, we stand on the threshold of discoveries that could fundamentally reshape our understanding of planetary formation, solar system evolution, and perhaps even the origins of life itself. The mysterious far side has taught us that even our closest celestial neighbor harbors secrets that can challenge our most fundamental assumptions about how worlds form and evolve. As we venture deeper into the solar system to explore other planets and moons, the lessons learned from far-side exploration will guide our understanding of the incredible diversity and complexity that characterizes planetary systems throughout the universe. The technological innovations required to unlock these far-side mysteries are pushing the boundaries of what's possible in space exploration. NASA's upcoming missions are being designed with capabilities that would have seemed like pure science fiction just a decade ago. Advanced artificial intelligence systems will guide rovers through treacherous terrain while making split-second decisions about which samples to collect and which geological features to investigate more thoroughly. These AI-powered explorers won't just be remote-controlled robots. They'll be sophisticated scientific partners capable of conducting complex analyses and adapting their mission parameters based on real-time discoveries. When communication delays make direct human control impossible, these systems will need to operate with a level of autonomy that rivals human scientific intuition. The sample collection technologies being developed for future far-side missions represent quantum leaps beyond anything used in previous lunar exploration. Next-generation drilling systems will be capable of extracting cores from depths of hundreds of meters, reaching materials that have remained untouched since the moon's formation. These aren't simple mechanical drills. They're precision instruments equipped with real-time chemical analyzers that can identify promising samples before they're even brought to the surface. But perhaps the most ambitious technological development involves the creation of permanent infrastructure on the far side that will support ongoing scientific operations. Engineers are designing modular habitat systems that can be delivered by cargo missions and assembled robotically, creating research stations that could operate continuously for decades without human presence. These stations would be equipped with laboratories capable of conducting detailed sample analysis on site, eliminating the need to wait months or years for materials to be returned to Earth. Advanced communication arrays would maintain constant contact with Earth through relay satellites, while power systems utilizing both solar panels and small nuclear reactors would provide reliable energy even during the 14-day lunar night. The scientific instruments being planned for these permanent installations push the boundaries of miniaturization and automation. Electron microscopes small enough to fit in a briefcase will provide atomic-level analysis of samples. Mass spectrometers will identify chemical compositions with precision that rivals the best Earth-based laboratories. X-ray diffraction systems will determine crystal structures and mineral compositions automatically. What makes these developments even more remarkable is their potential applications beyond lunar science. The technologies being created for far-side exploration will directly enable missions to Mars, the asteroid belt, and the outer planet moons. The autonomous operation capabilities, advanced sample analysis systems, and robust communication networks represent solutions to challenges that affect all deep space exploration. The economic implications of far-side exploration are beginning to capture attention from both government agencies and private industry. While the initial focus remains on scientific discovery, the resources potentially available on the far side could transform space-based industry in ways that seem almost unimaginable today. The extensive lava tube networks we've discovered aren't just scientifically fascinating. They represent ready-made industrial facilities that could house manufacturing operations, research laboratories, or even human habitats. These natural chambers provide protection from radiation and micrometeorite impacts while maintaining relatively stable temperatures, creating ideal conditions for activities that would be challenging or impossible on the lunar surface. Some visionary engineers are already designing systems that could utilize the unique conditions within these lava tubes for advanced manufacturing processes. The vacuum environment and low gravity could enable the production of materials and structures that are impossible to create on Earth. Ultra-pure crystals, perfect spheres, and complex alloys could be manufactured using techniques that take advantage of the Moon's unique physical environment. The mineral resources potentially available on the far side represent another frontier for space-based industry. The impact processes that created the heavily cratered landscape also concentrated valuable materials in accessible locations. Future mining operations might extract rare earth elements, precious metals, and other resources that are becoming increasingly scarce on Earth. But beyond traditional mining, the far side offers something even more valuable: access to materials that don't exist naturally on our planet. The impact melts and shock-processed materials created by ancient collisions represent entirely new categories of substances with properties that could revolutionize technology and industry. Some of these impact-created materials display unusual electrical, magnetic, or structural properties that result from the extreme conditions during their formation. Laboratory studies of similar materials suggest they could have applications in everything from quantum computing to advanced energy storage systems. The water resources potentially available on the far side present perhaps the most significant economic opportunity. While we typically think of the lunar poles as the primary locations for water ice deposits, recent discoveries suggest that some far-side craters may also harbor significant ice reserves, protected by the same magnetic anomalies that shield them from solar wind erosion. Water on the moon isn't just valuable for human consumption, it represents rocket fuel, radiation shielding, and the raw material for creating breathable atmospheres. The ability to access water resources on the far side could enable entirely new categories of space missions that would be logistically impossible if all water had to be transported from Earth. The strategic implications of far-side capabilities are also becoming apparent to space agencies and military planners around the world. The radio-quiet environment that makes the far side ideal for astronomical observations also makes it valuable for communications and surveillance applications that require freedom from terrestrial interference. Future communication systems based on far-side infrastructure could provide secure, interference-free links between Earth and deep space missions. Military satellites positioned in lunar orbit could monitor activities throughout the Earth-Moon system while remaining largely invisible to ground-based detection systems. The scientific discoveries emerging from far-side exploration are also influencing our understanding of other worlds throughout the solar system. The complex geological processes we're uncovering on the Moon's hidden hemisphere provide new frameworks for interpreting observations of Mars, Venus, and the large asteroids. The evidence for prolonged geological activity on the far side is particularly relevant to understanding Mars, which shows signs of volcanic activity that persisted much longer than simple thermal evolution models would predict. The mechanisms that kept the lunar far side geologically active for billions of years might also explain how Mars maintained its dynamic geology long after conventional models suggest it should have become inactive. Similarly, the magnetic anomaly patterns discovered on the far side provide new insights into the magnetic histories of other planetary bodies. Mercury's complex magnetic field structure might result from impact processes similar to those that created lunar magnetic anomalies. Venus's lack of a magnetic field might be explained by different impact histories or internal evolution patterns. The asteroid belt represents another frontier where far-side discoveries are influencing exploration strategies. The largest asteroids, like Ceres and Vesta, likely experienced impact processes similar to those that shaped the lunar far side. Future missions to these bodies will search for similar magnetic anomalies, subsurface structures, and preserved impact materials. The techniques developed for analyzing Chang'e 6 samples are also being applied to meteorites that originated from Mars, the asteroids, and possibly even more distant sources. These comparative studies are revealing that the processes we're discovering on the far side may be universal features of rocky world evolution throughout the solar system. Recent analysis of Martian meteorites using methods developed for lunar far-side samples has uncovered previously unknown details about Mars's early magnetic field and internal structure. Some of these meteorites appear to contain magnetic signatures similar to those found in far-side materials, suggesting that impact-generated magnetism played a role in shaping the magnetic history of Mars as well. The ongoing revolution in our understanding of the far side is also influencing theoretical models of planetary formation throughout the universe. The discoveries we're making about lunar evolution are being incorporated into models that predict the characteristics of rocky planets orbiting other stars. The extended geological activity revealed by far-side studies suggests that rocky planets might remain geologically active much longer than previously thought, potentially extending the periods during which they could maintain habitable conditions. This has significant implications for astrobiology and the search for life on exoplanets. The magnetic anomaly patterns discovered on the far side are also influencing models of how planetary magnetic fields evolve over time. The evidence for multiple magnetic recording events suggests that planetary magnetic fields might be more dynamic and long-lasting than current theories predict. These insights are particularly relevant to understanding the habitability of rocky exoplanets. Magnetic fields play crucial roles in protecting planetary atmospheres from stellar wind erosion and cosmic radiation. If the processes that created lunar magnetic anomalies are common on rocky worlds, then planets might maintain protective magnetic environments longer than previously thought possible. The subsurface structures discovered on the far side are also informing models of planetary interiors throughout the universe. The complex networks of cavities, dense regions, and heterogeneous materials, revealed by gravitational mapping, suggest that planetary interiors might be far more architecturally complex than simplified models assume. This complexity could have profound implications for understanding how planets generate magnetic fields, maintain geological activity, and exchange materials between their surfaces and interiors. The far-side discoveries are essentially providing a detailed case study of planetary interior evolution that can be applied to understanding worlds throughout the cosmos. The educational impact of far-side discoveries is inspiring a new generation of scientists and engineers who are growing up with an understanding that even familiar objects can harbor profound mysteries. Students who learn about the Moon's hidden hemisphere understand from an early age that scientific knowledge is provisional and that new discoveries can fundamentally change our understanding of the natural world. This lesson extends far beyond planetary science. The far-side discoveries demonstrate how technological advances can suddenly make previously impossible investigations routine. Students today are witnessing firsthand how innovations in robotics, artificial intelligence, and space technology can open entirely new frontiers for scientific exploration. The international collaboration required for far-side exploration is also providing models for how complex scientific challenges can be addressed through cooperative efforts that transcend national boundaries. The success of China's Chang'e 6 mission has inspired collaborative proposals for future missions that would combine the capabilities of multiple space agencies. NASA's Artemis program includes provisions for international partners to contribute instruments, expertise, and even crew members to far-side exploration missions. The European Space Agency is developing specialized drilling systems that could be used on future sample return missions. Russia and India are planning their own far-side missions that would complement and extend the discoveries made by earlier missions. This collaborative approach recognizes that the challenges of far-side exploration exceed the capabilities of any single nation or agency. The technological requirements, financial investments, and scientific expertise needed for comprehensive far-side investigation require international cooperation on a scale that mirrors the collaborative efforts that built the International Space Station. The long-term vision for far-side exploration extends far beyond scientific discovery to encompass the establishment of permanent human presence on the Moon's hidden hemisphere. While the initial missions will be robotic, plans are already being developed for crewed missions that would establish research stations and eventually permanent settlements. The unique conditions on the far side, the radio-quiet environment, abundant mineral resources, and natural shelter provided by lava tubes make it an ideal location for activities that would be difficult or impossible elsewhere in the solar system. Astronomical observatories, industrial facilities, and research laboratories could all benefit from the far side's special characteristics. The establishment of permanent human presence on the far side would represent a crucial step toward becoming a multi-planetary species. The experience gained from living and working in the challenging lunar environment would provide essential preparation for eventual missions to Mars and other destinations throughout the solar system. But perhaps most importantly, far-side exploration is teaching us that the universe is far more complex, dynamic, and surprising than we ever imagined. The Moon, our closest celestial neighbor and constant companion for billions of years, has revealed that even the most familiar objects can harbor secrets that challenge our fundamental assumptions about how the cosmos works. As we continue to explore the far side's mysteries and plan increasingly ambitious missions to unlock its remaining secrets, we're not just learning about the Moon, we're discovering new ways to understand the incredible diversity and complexity that characterizes worlds throughout the universe. The hidden hemisphere has become a window into the profound mysteries that await discovery wherever human curiosity and technological capability can take us. The journey to understand the Moon's far side represents humanity at its best. Curious, ingenious, and determined to push the boundaries of knowledge regardless of the challenges involved. Each new discovery builds upon previous findings while opening entirely new questions that will drive exploration for generations to come. The mysterious far side has taught us that the universe never stops surprising those bold enough to look beyond the familiar and venture into the unknown. The most extraordinary aspect of our evolving understanding of the far side lies in what it reveals about the fundamental nature of exploration itself. Every answer we uncover spawns dozens of new questions, each more fascinating than the last. The samples collected by Chang'e 6 aren't just rocks and soil. They're fragments of a cosmic puzzle that's been waiting 4.5 billion years for us to piece together. Consider the profound implications of what we're discovering about planetary memory. The far side appears to preserve records of events that occurred during the solar system's most chaotic and violent period, maintaining detailed geological archives that have been completely erased from more active worlds like Earth and Mars. It's as if the Moon's hidden hemisphere serves as a natural museum, carefully preserving exhibits from the cosmic catastrophes that shaped our planetary neighborhood. The magnetic anomalies scattered across the far side landscape tell stories that read like chapters from an epic cosmic novel. Each magnetic signature represents a moment frozen in time, the exact instant when molten metal from an asteroid impact cooled below the critical temperature and locked in the direction of whatever magnetic field existed at that moment. These aren't just geological curiosities. They're compass needles pointing toward magnetic north as it existed billions of years ago. What makes this even more remarkable is that we're essentially reading the magnetic autobiography of the early solar system. The strength and direction of these preserved magnetic fields provide clues about the Sun's ancient magnetic activity, the presence of planetary magnetic fields that no longer exist, and the complex electromagnetic environment that characterized our cosmic neighborhood during its formative years. The subsurface architecture revealed by gravitational mapping presents another layer of mystery that challenges every assumption we've made about planetary interiors. The Moon isn't the simple, layered sphere that textbooks have depicted for decades. Instead, it's a complex three-dimensional puzzle of dense and less dense regions, hollow spaces, and interconnected structures that suggest a far more dynamic evolutionary history. The Moon's far side has shattered every assumption we held about our cosmic companion, revealing that even the most familiar objects harbor secrets that can rewrite the fundamental laws of planetary science. From ancient creep basalts that challenge lunar formation theories to magnetic anomalies preserving 4-billion-year-old cosmic memories, each discovery proves that the universe never stops surprising those bold enough to venture beyond the known and explore the mysterious.